bio. Mordecai-Mark Mac Low is a New York City native who went to Stuyvesant High School. He received physics degrees from Princeton and the University of Colorado at Boulder, and then held postdoctoral fellowships at NASA's Ames Research Center and the University of Chicago before becoming an assistant group leader at the Max Planck Institute for Astronomy. He returned to his native city as a curator in the newly founded Department of Astrophysics of the American Museum of Natural History, where he is now the chair of the department. He has led 2 Haydn Planetarium space shows, was one of the founders of the museum's Master of Arts in Teaching degree program, and is one of the leaders of the open space software development effort to produce 3D time-dependent visualizations of the universe that can be run on personal computers or planetarium domes. With that, I'm going to turn it over to you.
However, host has disabled participant screen sharing. So while you're working on that, I will just reiterate my welcome. Go ahead and let's see, if you're on screen online, just go ahead and hit the raise hand button. I've got you all out in the gallery here. Yes, Michael, like that. Do you have a question? Okay.
No, I don't. No, I don't. Sorry. You just said press the button, so I did.
Excellent. Thank you for demonstrating that it works. The folks on in the room, someone should probably like watch them and raise hand on that screen, because I can't actually see people's hands. Yeah, like that. Good. Okay. And Robert's just raising his hand just to be a wise guy. Thank you. You have a question? Okay, I can see that. Great. You're welcome to use your camera. That way I can see if you're getting it or not. And that's always helpful when I'm giving a big complex presentation like this. I will probably burn up everybody's wires. If the frame rate starts stuttering too badly, you can ask me to run it again, run some of the video again. And let's take it away. Let's see, do I have share screen permission now? Yes, I do. Excellent. Hang on just a sec. Okay. And oh boy. I see the problem. Hang on for technical difficulties. We're going to try that again. Play first, then screen share. Perfect. Almost perfect. You can all see the title? Wonderful. Here we go. Okay. So how the Milky Way got its dark spots. So here is our glorious galaxy. Seen from within. This, of course, is a all sky image of our galaxy from the European Southern Observatory. And sure has a lot of dark spots. And of course, we can see those as gaps and holes in the Milky Way. And when they were first considered seriously, it wasn't entirely clear whether they were actually holes in the stellar distribution or things in front of stars. But it eventually became clear that you could see stars getting fainter and fainter as you went towards the centers of these things, demonstrating that they were, in fact, objects in front of a background star field. So if we go to the Gaia survey of the sky, you can do some fun tricks and zoom in on clouds. So this is a publicly available website. The Gaia archive visualization gives you the position you're pointing at. You can see my mouse, right? Yeah, good. Okay, gives you the position you're pointing at, field of view. This is a nice half sky or quarter sky view, but then we can start zooming in on the clouds. And we find that these things are incredibly structured. As we get to finer and finer detail, we simply see more and more structure. And it turns out that that structuring goes down to smaller scales than is resolved in this map even. So this is getting down towards probably 1/10 of a light year scales. And yet we're still seeing essentially continuously evolving structure. Getting down to 100ths of a light year, you might actually see a change. And we'll talk a little more about that as we get further along. Okay, so what are these dark spots? Well, to think about them, we'll start by thinking about where did baryonic material, regular stuff made of protons and neutrons and electrons, not that weird dark energy and dark matter that we don't know what it is, but it's dominating the universe. But how did the regular baryons get into the galaxies? Because surely these dark spots are made of baryons. So there we go. If we think about the early universe, it was extremely smooth. All the gas and all the dark matter was uniformly distributed, down to perturbations of a few parts per million. But those perturbations started to collapse. And in this visualization of dark matter collapse, that collapse proceeded, pulling the baryons with it. The baryons should pretty much just go along for the ride until they're concentrated in the centers of dark matter clumps, when they can actually start feeling enough pressure to resist the gravity of the dark matter. But they still, excuse me, keep collapsing and eventually cool down, go to very high density, keep collapsing and form stars. In this visualization, this is only including dark matter, and we simply lit up, turned on the lights in the centers, in the highest dark matter concentrations to simulate how galaxy formation would proceed. However, if we think about an actual galaxy, like this prime example, M51, the whirlpool galaxy, this is a galaxy that inside the galaxy is at least as much dark matter, it's at least as much regular matter as dark matter. So now the gravity of regular matter starts to become important to what's going on. Dark matter is still dominating the very largest scales, the rotation curve of the galaxy, the biggest scales, but the spiral arms, the gas clouds, those are all dominated by regular gravity of regular matter. And that means that gas physics and stellar dynamics is what's determining what's going on. So let's connect this to the picture we have of the Milky Way. Okay, we're looking at this galaxy. It's a disk galaxy like the Milky Way, a little bit smaller, but it's face on. Now, the Milky Way, of course, is edge on. We're viewing it from inside, looking along the plane. When all the stars we see essentially with the naked eye, unless you're really good and can see Andromeda or the Magellanic Clouds, all the stars we can see are in the galaxy. So even when you're looking out perpendicular to the disk, you're still seeing the stars that are above us in the disk, which is hundreds of light years thick. On the other hand, it's tens of thousands of light years wide, and therefore the line of sight through the disk sees a whole lot more stars from a much greater distance because you add them all together, and that's why it's brighter. Okay, so here we are looking at a galaxy face on, and we're seeing both starlight, and overlaid on the starlight is a map in the infrared that traces the dust emission. And that's the red color on here. So to separate that out, we can actually look in different wavelengths. So here we have a combination of visible light on the left, okay, showing the clouds as dark, absorbing the visible light. But here we're looking at this in radio wavelengths and looking at the emission from one of the most common and brightest emitting molecules, CO, carbon monoxide, which is made up of two of the most abundant elements in the universe, aside from hydrogen and helium, carbon and oxygen, the third one, of course, being nitrogen. These are the three elements that stars make after they finish burning their hydrogen and helium. Okay, if we look at CO, we see that it's exactly tracing these dark arms, these dark clouds. And that tells us that this is very dense gas, because CO can't form in the diffuse space-filling interstellar medium. That gas is ionized by the hot stars and therefore heated up to 10,000 degrees or even higher by supernova shocks, and dust can't survive in it. On the other hand, in the densest gas, dust can survive and accumulate. And even though this is a small amount of dust, it's like 1% as much dust as molecular hydrogen gas, that is enough over light years of distance to block out light through the clouds. So they become opaque to visible light. However, these dust grains are so very small that infrared light, particularly longer wavelength infrared light, can slide right by them. The dust grains are smaller than the wavelength of infrared light, and so it's transparent to infrared light longer than a few microns. And that's essentially the thermal infrared that we even know on the Earth, which is 5 microns. And then you can go out to tens of microns. Once you get beyond a couple hundred microns, everything is pretty transparent. And you can see stars that are forming even deep inside dense clouds of dust. Okay, so to try to understand how these clouds of dust that are blocking the light, forming the dark spots when we look through the Milky Way horizontally, how did they come to be? We did simulations. And this was a simulation for anybody who's interested in the technical details. We used a Voronoi mesh to follow gas flow around a bunch of particles. What this does in practice is allow us to do a whole galaxy with extremely high resolution in the dense clouds. So this galaxy is 90,000 light years across, and yet we can resolve the densest clouds down to less than a quarter of a light year. If we resolve, so on the left, I'm showing what we call the column density, how much gas there is along the line of sight. And on the right, I'm showing the temperature. So the highest temperatures are 1,000,000 degrees Kelvin. And that's gas that was heated up by hundreds of kilometers per second shock waves blasted out by supernovae. The cold end of the scale down here in the dark is 10 Kelvin, which is, I have to say, equally uncomfortable. We can reference Robert Frost. Would you prefer to die by fire or by ice? we would like to live up in here in the, orange at a few hundred kelvins, let's say 300 Kelvin, shirt sleeve weather. This is a log scale, notice. So from 300 Kelvin to 3000 Kelvin is just a little bit change in color here. Okay, so let me show you how the simulation looks. And bear in mind that this is a simulation of a galaxy strongly reminiscent of the whirlpool. And so there's a secondary. I'll back up a moment. This guy here, it came sliding by the whirlpool and is in orbit, but its gravity has caused the grand design that we see in the whirlpool spiral arms to form. And so we did the same thing. We stuck in a secondary, and you'll see it just as a white dot entering the scene, but it pulls on the main disk, and you'll see the beautiful grand design spiral arms forming from the action of that secondary. And you'll also see on the right that star formation proceeds apace. And as the stars form a few million years later, notice that we're running for hundreds of millions of years, a few million years after stars form, the biggest, brightest ones explode as supernovae, driving million-degree white-yellow gas out through the galaxy. So let's watch that. So you can see these blast waves spreading hot gas around as star formation occurs. Meanwhile, these cold, dense clouds are continuing to collapse and form new stars. Here comes the orbiter, and now you can see it driving further star formation. We're getting hotter because gravity is pulling the gas together in these grand design spiral arms, and the orbiter is producing much more structure than we had in the quiescent galaxy. And we're coming up on the point at which we actually observe the whirlpool, which is about now, when the orbiter is at the end of one of the spiral arms. And now we're going into the future, so to speak. You can see that the galaxy has produced a halo of million-degree gas, and we see these halos from their X-ray emission because they're so hot that their thermal emission is coming out in the X-ray. And meanwhile, we see the cold clouds. We can compare directly the structure in these clouds to the structure in the molecular gas that I showed you in the previous slide, which was taken with the Plateau de Beer interferometer observing in the radio. So now we have an idea of how these clouds what the structure of these clouds is, and we know that it's controlled by the physics in the simulation because we can generally reproduce the observed properties with the simulation, but the simulation really was very simple. It had gravity, gas pressure, and star formation, supernovae. And that's sufficient to explain the majority of the gas dynamics. Okay, this is a model of two more equal massed galaxies running together and forming, all the red dots are globular clusters, million star clusters. And so this was actually a model to see how the gas collected into stars, but it also showed us how the gas behaved during this collision. Why am I showing you this? Because it was the basis for a model in which we took galaxies and took the stars in them and treated them as starlight, and gas in them and treated it as gas and dust. And so we can actually see what the dust does to the starlight looking at the galaxy. And look at this galaxy edge on. Let's back that up just a little. Okay, look at that galaxy edge on. It's extremely thin, and it's got a beautiful dust lane down the center. And that is exactly what we see when we look at the Milky Way. Now here it is face on, and you can see how the dust is tracing the spiral arms. Now, of course, they ran into each other and pulled, the gravity of each galaxy pulled stuff off the other. And drives lots of extra star formation. We get a starburst and a peculiarly shaped galaxy, as Halton Arp would have called it when he made a catalog of these things. But again, you can see how dust lanes are a natural consequence of gas and gravity. Okay, if you have a gas that's in a disk, in a stellar disk, the gas collapses down because it can cool. It's got all these emission lines. It gets dense, it absorbs light, and when we see through it, we see the star-forming clouds, which are the dark spots. And that's the secret, is that these dark spots are really the places where stars form. So here's a close-up of a dark cloud in Taurus. Okay, it's up here, like a little between Aldebaran and the Pleiades. This is just one small piece of the dark clouds in Taurus, which is one of the closest regions where stars form. This is invisible light, okay, and you can see it absorbing light, but you can see how stars shine through. You can see some stars that are brighter shine through, but are reddened by the dust. The longer wavelength red light can get through the cloud easier than the blue light that gets scattered. Just like in the Earth's atmosphere, the blue light gets scattered all over the place, but the red light punches through. And so we get sunsets and blue skies. Well, here, the dust scatters the blue light, but we can still see the red light or the infrared light from stars that are shining through. And that's in astronomical terms called reddening for obvious reasons. Now, what happens if we look at this in the radio? Okay, now we're looking at dust emission with the Atacama Large Millimeter Array. This was actually a pathfinder for it. And now what we see is that the dust lights up in exactly the dark regions, but here are the young stars starting to form. These are the regions where gravitational collapse has collected the gas and dust together, making it much brighter because it's much denser. And there may even be young stars inside these regions starting to heat them up. Although you sure can't see it in the visible, right? Just not there. Because if there's a star in there, it is completely obscured in the visible, but it's still heating the dust. And so it's producing infrared thermal radiation that can get out and be seen in the millimeter. Okay, zooming out a little. So that was this region right in here. Now, these are two different views of the entire Taurus star-forming region, which is one of those little dark spots in the Milky Way if you look towards Taurus. This is in CO, carbon monoxide, showing that the structure of the surface of the dense region, because the carbon monoxide becomes opaque as you go towards the center, because there's so much of it that it can actually absorb all the light in its absorption lines. Now, if you go to the dust, okay, you can, oops, sorry. If you go to the dust, you can see into the centers of those clouds and see the dense regions. And so now you see what the densest parts of the clouds look like. And they're much skinnier, which I will show in the next sequence is a consequence of gravity. Gravity acting on big clumps of matter makes filaments. And that's true whether it's dark matter on the cosmic Webb scale or collapse into individual clouds. Okay. So let me turn to a modeling effort. It was led by my PhD student, Juan Ibanez Mejia. So we took a section of a disk galaxy. Here's a typical disk galaxy. And that section was 60,000 light years tall, but only 3,000 light years wide. I'm giving it to you here in kiloparsecs. Parsecs are a little over 3 light years. And we put this on a computer. Okay, so here I'm showing column density again, how much gas is along the line of sight, looking down from above and looking at the innermost part of that box from the side. Okay, so here's the midplane of the galaxy. You are here in the galactic midplane, and you're looking at how much gas is along the line of sight here. And here you're looking down from very, very high up. A vantage point we'll never reach. And we let supernovae go off. Now, in this model, we did not include self-gravity. We only included the gravity of the stars, but the gas can't pull on itself. And that will turn out to be important. And we'll see in a moment. But meanwhile, what we saw is that the supernova explosions cleared out huge bubbles, cavities of gas that was far less dense than the average interstellar gas. Now, mind you, all this by terrestrial standards is an excellent vacuum, but the material in red might reach densities as high as 1,000 or tens of thousands of particles per cubic centimeter, while the blue regions might only have an atom, a particle per cubic meter. Well, the difference between a cubic centimeter and a cubic meter is actually enormous. So these are quite different densities, even though the best lab vacuums might have 1 million or tens of millions of atoms per cubic centimeter. So yeah, this is a great vacuum, but it's still dense enough that it behaves like a gas over light year scales, because the mean path for the particles to hit each other and thus generate a pressure is only about 1/4 of a light year. So it actually acts like an ordinary terrestrial gas with winds and sound waves and shock waves if you observe it at large enough scale. And thousands of light years is large enough scale. Thank you very much. So the supernovae blew apart this gas, concentrated it, because when you compress interstellar gas, it tends to radiate, and that cools it off, and that makes it extremely compressible, far more compressible than, say, the Earth's atmosphere. And you get actually large, dense clouds. These are clouds that at first glance appear to be similar to the observed clouds. They're dense, they're tens of light years across, they sit around for a while. And that was very intriguing. And so I thought and suggested to my student that these might be the basis for long-lived dark clouds like we observe in the Milky Way. Well, we haven't been around long enough to see if they're actually long-lived. If we look back to when the dark clouds were first shown to be full of high-density molecular gas back in the early 70s, a great debate sprang up that's been going on pretty much ever since. Are these objects, the things we see as dark spots, are they long-lived, 100-million-year-old objects? Or are they transient, foam on the waves of the interstellar medium that comes and goes every few million years? Well, this ran, for tens of millions of years. And if you look at some of these clouds, they lasted that long. And so my first instinct was to say, oh, the people who argue for old, long-lived clouds must be right. But then we added gravity. And in the next simulation, we'll look at how this behaves with gravity. Okay, so the long-lived cloud argument is the clouds form from supernovae, get pushed together, gently gravitate, but they're stirred so heavily by some combination of supernovae and other processes that they resist fast collapse. And they just sit here as more or less quasi-static objects. This would be consistent with the observation that they don't form most of their gas into stars. If they did, the Milky Way would be forming stars at a tens or even hundreds of times faster rate than it actually is, which is only like 1 solar mass per year currently. So we did this simulation. This is again, edge on and face on. This is now after the supernovae have been stirring it for a while. They've made a bunch of big clouds. This thing here is a zoom in of this object here, okay? Just so we can see it a little better. And if the hypothesis that these are long-lived objects had been correct, we would have turned on self-gravity and things would have gently changed. You would have gotten a little bit of collapse, but everything would have stayed more or less the same. So let's watch what happens over a simulation of 6 megayears. Remember, the previous one ran for 200 megayears. Here we go, 6 megayears. What happens? Does it stay the same? Oh, no, it really doesn't. If we look at the zoom in, it's just collapsing into filaments like crazy. What happened here was it turns out that the supernovae exploding in this extremely low density gas, they cannot stop the high density gas from collapsing under gravity. And so that just goes ahead and collapses. And remember what I said about gravity makes filaments? There it is. Okay, the gravity takes this diffuse cloud and makes sharp filaments out of it. Do we see that in the real ISM? I'm sorry, in the real interstellar gas, interstellar medium? Yes, yes, we do. This, known as Nessie, is a 70 parsec, 210 light year long cloud of extremely dense gas. It is so dense that it's even opaque in the near infrared. Okay, you can see this as a dark cloud, an infrared dark cloud. And that means that the densities got extremely high in the center. And this is in the center of a larger visible dark cloud, okay? However, what we see at points along here is bright emission from stars. If you look off in like 200 or 300 microns in the thermal in the Herschel band, we see these stars lighting up and we see the dust, which might be 10 or 20 Kelvin, emitting in this long wavelength infrared light. So now it's lit up instead of obscuring background starlight. This looks like the signal of gravitational collapse, first forming the filament and then forming individual stars or star clusters along that filament. If we take one little piece of that larger simulation that I showed you and watch its collapse, okay, so now we're in a 300 light year box. And we zoomed in here to 0.4 light year, 0.36 light year resolution of the simulation. Okay, now the dark line is just outlining the dense gas in the cloud. And that emphasizes how it's collapsing gravitationally, even though there's all this action going on around it, driven by multiple dozens of supernova over the 10 million years that this cloud evolves. So what happens inside those dense collapsing regions? We can zoom in further and simulate just the innermost few light years of one of these clouds. And we did that with a model. that includes the stars explicitly, star by star. In this model, in this visualization, the little dots are barely bigger than brown dwarfs. A big blue dot is around 80 or 100 solar masses. So there's a big blue dot, and that thing is emitting ionizing radiation, 1,000 km/s stellar wind, and it blew the gas apart and produced these distinctive shapes on the sides, these pillars. And you will see observations that once you see them, you'll say, oh, that looks familiar, that are exactly produced by this sort of pillar production. Okay, look at these. And you can see this whole bubble is being blown apart by the hot star. And then another hot star forms at the edge just as we end the simulation. If we watch that in temperature, so that, I'm sorry, that was in column density. So just showing where the gas along the line of sight went. And that bubble was inside a bigger, denser cloud, which is why the contrast wasn't so great. Now, if we look at the temperature, it starts off cold, 10 to 100 Kelvin, okay? Then as stars form, it heats up to maybe 1,000 Kelvin just from starlight. But then watch what happens when the hot star comes on. We'll see it ionizing gas out to blue, 10,000 Kelvin, and heating it up with shocks from the wind to 1,000,000 Kelvin or more, several million Kelvin. So there's the stellar wind bubble. This is the freely flowing stellar wind, the inner shock that heats it to 1,000,000 Kelvin, and it pushes out against the ionized gas. And nearly all the gas gets heated up in the end by the huge amounts of ultraviolet radiation coming off this hot star. And that's key, because that is why these dark clouds die. They get ionized all to heck by a hot star that has formed from gravitational collapse. Okay, I promised you I would show you something that looked like those pillars. Well, here it is. This is the Eagle Nebula. And here you have exactly those sorts of pillars driven by the hot stars in the center of this OB association. And if we zoom in on this one, that's the iconic pillars of creation, formed by ionizing radiation, interacting with dense gas. There are stars forming in these pillars. If you look closely at them with the infrared, you actually see little jets coming off from the young stars. That's exactly what's going on here. To see this structure in 3D, Stefan Reisel developed the Polaris Code that allows you to visualize this sort of model, in this case, a model by Daniel Seyfried, and we can rotate it and see how the dust lanes completely depend on what direction we're viewing it from. If we're looking through the clouds, they're very red. If we're looking across them, they just are slightly obscuring. Whoops, sorry, let's run that again because it's kind of fun. Over on the side, we're showing magnetic fields and polarization, all sorts of stuff. But the point is that these are the sorts of structures that happen when stars form in a dense dark cloud. So those dark spots are the source of the rest of the Milky Way, because every star that we see across the Milky Way formed in one of those dark clouds at some point in the history of the Milky Way or of its progenitor galaxies, because the Milky Way didn't form at its current size. It formed from a combination of smaller galaxies merging together and gas falling onto it and forming into stars directly. Since the last major merger was over 10 billion years ago, a lot of the more recent history has been gas and tiny galaxies like Sagittarius falling onto the Milky Way. But we can still now today trace remnants of ancient galaxies that are still circling through the Milky Way's star fields, but have their own distinct compositions and their own distinct dynamics left over from the orbit when they came in. The Gaia and Enceladus galaxy is one of those. Okay, well, there's all this gas collapsing into stars and forming ionized gas. If you look at observations of this ionized gas, so bright nebulae like Orion, you start to see little dark spots silhouetted against the gas. These are protoplanetary disks, sometimes called proplyds, which is just a not very good acronym for protoplanetary disk. And they are, again, much smaller dark spots, but formed by the same mechanism. Dense gas with lots of dust in it, or dust in it at typical interstellar abundances, say 1% of the gas, that is so dense that it's optically thick in the visible. It's opaque in the visible. And therefore, it blocks light emitted from the background nebula. And we see it as a silhouette, or sometimes we even see a dense ionized rim on the front of it, and then the back of it silhouetted. These are disks of gas that is forming into young stars, and around those young stars are planets. So this is a rogues gallery of these young silhouetted disks. And of course, we can now observe disks other ways as well. So if we look at one of these disks, we actually see light shining out. Now that's not the star itself, but what it is there's a central, extremely young star, maybe 0.1% of the lifetime of the sun or less. And that star, the light is shining out through the disk and getting scattered towards us because there's a central hole in the disk carved by the star. So we're seeing the starlight shining out and getting scattered towards us. How do these disks and stars form? If we zoom in to a model of the formation of a small cluster like this, now this doesn't include any massive stars, so we're just going to see where the low mass stars form. And now this is only a few light years across, and the yellow bright is dense gas, while the white dots are stars and even brown dwarfs. And we see this, again, filaments forming, brown dwarfs forming. The special thing about this model is it included the heating from these smaller stars. So if we look at the temperature, which starts off really cold, 10 Kelvin, and then stars start forming, well, the first star doesn't do much, first few don't do much, but then you get slightly more massive stars, and they start heating up the gas. Heating up the gas already limits how quickly stars can form from that gas, because it increases the pressure and that makes it harder to collapse. And so this is already limiting the amount of stars that can form just from these puffs of radiation that come out from these young stars. Now, all these stars formed with little disks around them. And so here is a rogues gallery of the disks that formed around every one of those sync particles, every one of those particles that started to every one of those young stars. That's essentially what's going on here. And what you see is a wild variety of different disk histories. Some of them, after a while, will stop accreting, and you'll just see the star naked in its little square here. So this is just a little cutout around every one of the stars in that previous simulation. And you can see disks with spiral arms, like thinking they were galaxies. You can see binaries in disks. You can see triple systems interacting with each other, even quadruple systems. All of this dynamics is going on during planet formation. And it is directly influencing the nature of the resulting planetary systems. So you see now some of these stars have lost their gas, but they presumably still have any planets that formed during the gas-rich phase. So we can observe these disks, and the best instrument in the world for observing them is the Atacama Large Millimeter Array, an international collaboration between the European Southern Observatory, National Astronomical Observatory of Japan, and the US National Radio Astronomy Observatory, funded by the US National Science Foundation. This is 64 large radio telescopes that can be moved around across a plateau at about 15,000 feet in the Atacama Desert in Chile. And if you move an interferometer apart, its resolution increases as if it were a single antenna as wide apart as the farthest separated telescopes. Now, its sensitivity depends on how many dishes you have, but the resolution depends on the distance across the array of dishes. So this is both high resolution, 64 dishes, and I'm sorry, high sensitivity, 64 dishes, and high resolution. And what does it do? It reveals wonders. For the first time, we were able to see structure in disks with forming planets. And this is structure that was predicted to occur from planets in disks, but also from other mechanisms. And so the grand challenge right now is to distinguish which of this structure actually comes from planets and which comes from other disk dynamics, spiral waves, vortexes, all sorts of stuff that could interactions, radiation. There's many, many ideas. This is how a planet can form this sort of structure. So let's see, did we get this going? Whoops, no, there's a little bit of an issue here with this simulation. How did oh yeah, I know how I got it going. There. So here is a planet. It's failed again. One more time. There. Now there we go. Okay. This is in the rotation frame of the planet. So we're following the planet around and keeping it fixed. And what it's doing is it's forming these spirals because the gas on the outside is being overtaken by the planet, while the gas on the inside is going faster than the planet. And as the planet drags on that gas, it pushes it away and opens up a gap. And this is why people look at these images from ALMA and say, are there planets forming gaps? So far, we've only found one planet in a gap in an object called PDS 70. And so there's probably other things going on. Clearly, one planet can form lots of structure. And so that's one thing. Here is a set of simulations that show how a single star in all detail forms, and then how a disk inside with multiple planets in it drives those planets and allows them to move around in the disk, because the interaction of the planet with the disk can actually change its orbit, cause it to come in or go out. And so here's the disk. There's a couple of planets, one massive enough to clear a gap. The other smaller one is just migrating. And the third one you can actually see going in a little. Again, these are very thin disks. In some sense, this is the same physics as a galactic disk. It's gas that cooled and got very thin, but it's on a much, much smaller scale. This is now solar system scale. And this is the physics that determines the architecture of planetary systems. Okay. I would actually guess that I'm kind of out of time. So maybe this would be a good place to stop and take questions, since you guys have all been sitting on your hands for the whole talk, which either means you fell asleep or were fascinated. I don't know which. But let me stop here and go ahead and take your questions.
Any questions out there? We had a couple in chat that were handled, I think, locally. Let's see.
Oh, yeah.
Jay asked if it was real time, so I didn't. Jay, would you like to open your mic and talk directly with Dr.?
Oh, hi. Yeah, I was just wondering when you were showing all of those different slides of the infrared, it looked like orbits or rotations.
Yeah. So the simulations were all done at extremely high rates, sort of, tens of thousands to millions of years per second. The observations were all still. Just point a camera at the sky and take an image. So in some sense, we only get a moment in time. While we're in astronomy, we're moving towards doing a lot of astronomy about things that change on human timescales, seconds, minutes, days, hours, days. The interstellar gas, which is spread over light years, takes millions of years to move, most of the time. I mean, sometimes there are actually phenomena that you can see in the very centers of star forming region that only take decades, which I've worked on. We can actually see flickering from ionized gas at the centers of star forming regions, but that's very much the exception rather than the rule. And even that takes, took Chris Dupree a good fraction of his career to follow. As a grad student, he took the initial images, and here he is, a senior astronomer, and can finally publish a paper on that particular topic. Luckily, he did a lot of other interesting things while waiting. Thanks for the question.
And then, if I may ask, this last galaxy that you were showing, is this a simulation or is it like I think it's called the Sombrero Galaxy?
Okay, this one is actually a simulation of a single protoplanetary disk. So this is galaxies might be tens of thousands of light years across. This is only a 10,000th of a light year across. 10,000th. So this is like our solar system.
Okay.
And so, you could imagine a huge galaxy spread out, but I can't simulate that because I don't have anywhere near enough computer time. Not at this resolution. I mean, the resolution of this simulation is far smaller than a single astronomical unit. And there are 150,000 astronomical units in a parsec. So 50,000 per light year.
Okay, I have a question.
Yeah.
At any point in the evolution of the universe, does dark matter turn into real matter or vice versa? Is there any interaction between these two forms of whatever makes up the universe?
Not since the first, few femtoseconds or something. We don't know before then. But what we know about dark matter is that it interacts extremely weakly at best with visible matter, photons, light, or anything else that we can perceive. How weakly it interacts, we're still trying to pin down. We hope that it interacts somehow besides gravity so that we can detect it and determine what it is. But so far, all we've done is place upper limits on how weak the interaction is. And we're kind of starting to get close to running out of parameter space that we could measure. Like a lot of the classic ideas about how to detect dark matter are limited by things like neutrinos hitting the detectors. And we're getting close to those limits. Another decade or so, and we've either got it or we've run out of space for those sorts of methods. Turning into regular matter, probably not in any significant quantity, because if it did, it would look essentially like a continuous formation universe, and that would have very different dynamics than the universe we see. The universe we see started out with no star formation, had a huge burst of star formation 12 billion years ago, and has been on a downward trend ever since. And so there are fewer and fewer stars forming because we're running out of gas. There's no replenishment, say, from a dark matter conversion source or any other sort of continuous creation, which is kind of a shame. We're well past the glory age of star formation, and it's an indication that dark matter isn't helping us.
We have a couple of questions from the in-person group here. Bring them
Great.
up one at a time. Okay, first, a couple of simple questions. You were talking about the carbon monoxide being detected by radio telescopes. Would you happen to know the wavelength of the carbon monoxide emission?
Yeah, so there are a bunch of useful lines. I want to say that the brightest one is at about 2 millimeters. So it's really not radio, but millimeter. Microwave oven wavelengths.
Okay, thank you. And another simple question, the large millimeter array that you were describing, I missed the size of the dishes.
64 dishes in the Atacama Large millimeter array.
And how big are those dishes, you know?
I don't know. I want to say they're about 50 meters, but I could be wrong by, actually, they're smaller than 50 meters. Let's go with that. But
Okay.
I don't remember the exact value.
Okay.
Yeah, no, sorry.
And finally, you showed how a supermassive star in the middle of let's say, a cluster of stars.
Yeah, you can say that.
And then it spreads the cluster out. Would that be, would the Pleiades be the result of that process, or are the Pleiades still evolving?
The Pleiades is very definitely a result of that process after the most massive stars have already gone supernova. So the Pleiades is tens of millions of years old. And so the most massive stars from that star formation event have already gone supernova, and the rest, the lower mass stars, are still surviving as an open cluster.
Okay, that's very, I really appreciate that, because when we show Pleiades star parts,
That's what was going on.
some fascinating facts, and there's one right there.
Absolutely. Absolutely. Great stuff. Others?
I was just kind of curious with the simulations, what kind of, how much hardware do you have to throw behind those to simulate the dark matter web of the universe? How long does it take to render something like that?
Yeah. So that particular model was run using a very clever trick that Tom Abel came up with, which was to realize that if you move into 6-dimensional phase space, velocity and position as independent axes, the dark matter starts out as a sheet because it's at rest. And so he actually followed that n-3 dimensional sheet through 6-dimensional space. And that vastly reduced the total amount of computation time that was required. So he took things that used to take many, many months and turned it into a few days for that simulation. But in general, these models run on anything from hundreds to tens of thousands of processors for days to months.
Yeah, they're really cool. I appreciate those. Thank you very much.
Absolutely.
Any other questions online?
Hearing none. Nothing in the chat. I probably have 80 that are going to show up at about 2 in the morning. I think. That was absolutely wonderful. Yeah, I think you've dried us out.
Okay.
That was wonderful. Thank you so much.
Yes, enjoyed it very much.
Absolutely. Thanks for all
It
the
was
questions.
great. I learned something, so that was good.
Absolutely.
Thank you.
Many of us did. I feel like I should run down to AMA Edge and find value for a coffee and we'll sit down and talk for a while. That was marvelous.
Well, sorry I couldn't join you guys in person, but
That's good. All.
This is terrific.
Yeah, this is terrific. It's comment from the crowd here.
great.
Wonderful. Hopefully we can hear from you again at some point. Let's see, we got some things showing up in the chat here.
Well, I'm down here.
I think it's all.
Now I'll just thank you very much. Very interesting. Absolutely wonderful.
Great.
All right.
Okay.
Well,
time.
we'll call that the end. We can stick around for a few minutes, I think, but most of us here are going to be ready to run out and see if we can put up a Squally's pizza. But maybe we'll hang out for just 5 or 10 minutes and see if anybody wants to chat about anything specific. Oops. Is the Rose Center currently open? Mordecai, are you still here? He may have dropped.
I think he's dropped off.
I think he dropped off.
I think it is still open.
I think it recently opened.
We'll have to look it up. All righty.